Hello, hello. All right, the Slido should be active. We're doing more heaps today, which you need for the assignment that went out this morning. So go ahead and get started on this. Let's talk about this in like 2 minutes. 2 minutes. So go ahead. Are these valid heaps? All right. In the interest of time, let's get started. I'm going to flip over to the Slido. Let's see where we're at. We only have 63 answers so far, and I know there's a lot more than 63 of you in this room. So, ooh, that silence tells me that everybody went, oh, I haven't signed on to the Slido yet, maybe. But let's see what the 66 of you have said. Aha, okay, so of our 3 heaps, we think the left one is valid and maybe not so much the right or the middle one. Yeah, seems interesting how those numbers change as soon as I expose everyone else's answers. Yeah? Okay, let's walk through them together. So reminder too, I know I said this before, but heaps are not on the midterm. They will be on the final exam, and they are the project that you're going to be doing that went out today, but these are not midterm topics. But we have to talk about them, so you can do the homework that just got assigned. Okay, so this heap on the very left, we've got 8 as the overall root. Its children are 9 and 10. Thumbs up, valid. Thumbs down, invalid. Thumbs up, I agree. This one is valid. Remember that what we are looking for is that for every node, it is smaller or equal to its children. 8 is smaller than both 9 and 10. We are also looking for completeness, which means that all nodes have both of their left and right children filled along the same level, moving from left to right. You do not start a new level until the previous level is totally full, and you only fill it from left to right. So looking at that middle tree there, thumbs up, thumbs down, valid or invalid. Ooh, yeah, okay. We've got some determined invalids on this one. Does anyone want to raise their hand and tell me which node invalidates this heap? Let's see. I'm looking for any more diversity of answers. I appreciate all of our wonderful regular participants. Yeah. The 4, absolutely. I agree. The 4 is the child of 5, but 5 is larger than 4, so the heap is invalid. The 4s ruin it for everybody. Okay, let's talk about the rightmost tree. Thumbs up, valid. Thumbs down, invalid. Invalid, I agree. Does anyone want to raise their hand and tell me why this one is invalid? Yeah, here. There's a hole next to the 5. In fact, yes, I think if I click this, there's that. Aha, there we go. Yes, there's a hole We had started the row with 22 while there was still space in that second row to give 3 a right child. There's also a second hole hanging off this 4. Does anyone have any questions about the validity of the heaps? Cool. Okay. All right, let's talk about some administrative stuff. So reminder that P2 is due tonight. However, I know that a lot of you know that P2 is due tonight because office hours have been wild. I know everyone loves the professor that's like, I told you so. I told you to start early. I told you office hours would be busy this week. It's okay. We're all human. Shout out to the TAs that have been trying to, literally, we call them bat signals when the office hours are really full. And so shout out to all our TAs responding to bat signals, trying to help out. We know the office hours earlier today were a little busy. I'm trying to get some more people to come to my office hours, which is sort of the last office hours before it's due this evening. If you can't get into office hours, keep in mind you can always post on the Ed board. I know it's way harder on Ed than it is in person. You also can always use a private post on Ed if you have any sort of last-minute questions. And one thing just to know is there is very possibly going to be a rush to run the tests in GradeScope as we get closer and closer to that 11:59 point. And there will come a time when GradeScope will stop running tests if there's too many requests. So try not to be the person running it 10 minutes before 11:59 because you could get in a situation with the servers, and I'm sorry, there's just nothing I can do about that. That's a GradeScope thing. P3, I think, was already released this morning. Shout out to the infrastructure team. P3 is implementing a heap. We are going to talk about how you do that all day today. Here's what I will tell you. I know I said P2 was a 2-week assignment, and we gave you 2 weeks, and you should have taken 2 weeks. I also know we're giving you a midterm on Friday, so P3 is, it's hard to say, right? We all do things at different times, but I will say P3 is historically a 1-week assignment. But we are going to give you 2 weeks to do it so that you can do other things. So I know P2 was a little, just so you know, P3 is probably not quite the same level of involvement as P2, though you get the same amount of time. I feel it's dangerous to say that because I'm sure in a week somebody's going to be like, Casey, no, it's terrible. You lied to us. But at least that's our intention, I promise. So it's due 5/10. Exercise 1 regrade requests, just so you know, are due on the 30th. The TAs will then start addressing the regrade requests. I also just want to take a moment here and pause. I know that a lot of the exercises are auto-graded. A large portion of the exercises are auto-graded, which makes it literally impossible for us to give partial credit. You kind of either get it or you don't. And I know that feels harsh, especially when you compare it to the projects where you get to run your code and then see exactly the response you get. And so you've got one aspect of this course that's group assignments. You see exactly what you get. And then exercises where it feels a little harsh. I promise you this is actually my attempt at kindness in that almost all of the problems that are on the exercises used to be on exams. And I thought, instead of forcing you to do it on an exam, we'll give you a whole week to do it in partnership with each other and your TAs and all the time you want, all that good stuff. But the grading on your exercises kind of reflects the grading we will do on the exam. So if you're also preparing for the exam, that fourth question, the last one where you usually are sort of writing an essay, that is similar in format to the style of question that will be on the exam. So that's the other way we're trying to give you some sort of awareness of what the exam's going to be like. That's also my attempt of saying, it's not the TA's fault, I'm the jerk, blame me. E4 is out. If you'll notice, E4 is entirely auto-graded. It's much shorter. It's because the TAs are going to be grading your midterm instead of grading your exercises this week. And then E5 will come out on Monday. But again, we want to give you a little bit of a break because we know that next week you're also going to be working on your midterm resubmissions. So E5 is kind of similar in that I'll say it's more like 1 1/3 weeks work, but we're going to give you 2 weeks to do it kind of thing. So I know this is an intense week. I know you probably have a lot of midterms this week and next. We're trying our best to balance the workload as best we can according to the schedule and still get everything out. And then finally, P4. So after this P3, P4 is your last programming assignment in this course. It will be I think it's at least 3 weeks. You have to do it. We'll have it due like the Wednesday of finals week. It is a hefty assignment, but you'll see like the amount of things that you got to get in kind of slow down after we get P4 out. And then the only thing I wanted to make sure that I announced as well is that the midterm resubmission, we're going to take the exam together here on Friday. Me and the TAs are literally going to scoop up those exams and immediately go start grading them. We will release the grades for your midterm on the following Wednesday, and you will have exactly 1 week to resubmit your midterm. You'll get a new assignment, you'll do it on GradeScope, and we will just regrade it. So it's like you get to take this exam 2 separate times, and in the middle, you get your grade back. And then we will average your 2 scores, which is the same mathematically as saying you can make up to half of the points you missed back. So keep in mind that you will have that extra bit of assignment if you would like to do the resubmission starting next week. And because of the nature of the grading for those things, we cannot accept late midterm resubmissions. So that is the one assignment you cannot use your late days on. Cool. Does anyone have, I know there's a lot of administrative stuff, does anyone have any questions? Yeah. There is not assigned seating. You do not need Scantrons. Yes. Sorry, say that one more time. Yes. In fact, we will only open up the resubmission after we release the grades. Those things are tied together. So you will get your grades, and then we'll say, go, you have a week to resubmit. Yes. There is an exercise 6, yes. I think it goes to 7, yes. Any other administrative questions? Yes? Will you see your So literally what we're going to do is we're going to take the pieces of paper you write on, we're going to upload them, we're going to scan them and upload them into GradeScope, we're going to grade them on GradeScope, we're going to release your midterm back to you. So you'll see the things you answered and the score that you got associated with each individual question, and then you get to retry it. So the intention is that you get to look at what you wrote, you look at what you got right, what you got wrong, and then you get a second shot at it, outside of the confines of the weirdness of a timed paper exam kind of thing. Yeah? If you are preparing for the midterm, which my wonderful head TA just told me, we have not seen a lot of conceptual questions coming into the ed board, which gives us a sneaky feeling that we're probably more focused on P2 right now than we are on the midterm. Like we said, we've been helping you sort of prep by giving you those questions and the exercises all along, but keep in mind that tomorrow in section, your TAs will be doing a review, so probably an extra good section to go to. And we have this tiny URL here that is a survey that will tell your TA what you want to specifically review in section. So if you want them to go over a specific topic or to go over a specific question or something like that, please fill out this tiny URL so your TAs can cater their plans for tomorrow's section to your needs. Also, we did add a new page on the website if you hadn't seen it. That's called Exams. That collects together all the exam practice materials and requirements and all that good stuff, so you don't have to go scrolling through the calendar. I'm going to slip over to the Slido right now because I'm going to guess there might be some more questions that maybe people don't want to say aloud. Let's see here. Oh, the slides are locked? Oh, thank you. Okay, thank you for doing that. Wonderful. When will exercise 2 be graded? You will get the exercise 2 grades on Saturday, and that'll be the kind of pattern where like the TAs have to wait for the last late day to close, and then they grade them, and then we will generally release those grades on Saturdays. And then calendar. Oh, thank you. Okay, thank you. We might need to double check that calendar. Thank you for calling that out. Any other questions? There's a new one. Will the question of makeup midterm be exactly the same? I assume you're talking about if you have an accommodation midterm, and I cannot guarantee you that the midterms will be the same. I also cannot guarantee you that, since they're not necessarily the same, that they will be of equal difficulty. That's not how that goes, unfortunately. Cool. Okay. Can you say there are no right answers? Oh, ooh, look at this. Oh, wow. Okay, thanks, everybody. That's why I figured we should do this. Will the exam have anything about red-black trees or left-leaning red-black trees? They will. You technically are responsible for all of the materials through Friday of last week. But for example, you don't need to know how to do the rotations. Like, I'm not going to give you an AVL tree or a red-black tree and ask you to rotate it. I might ask you to think about all of the different data structures you've learned about and think about how they could be used in a certain scenario and what the runtime impacts of them in any given design scenario might be. So you don't need to know the mechanics of those things, but you do kind of need to understand the implications of what they mean from a design perspective. Can you say there are no right answers for choose the right answer data structure questions as long as we define answer? Yeah, I will say, just so you know, technically correct always wins in my class. So if you can defend your answer, we will probably take answers that are, say, different than the ones we thought of, but I will tell you that it is very rare for a student to come to us with a design that we did not consider to be the right answer and for it to be perfectly equal in optimality and functionality to the one we came up with. So there are most optimal solutions, and there are ways to justify optimality. So for example, if you're like, I would pick linked list because I'd rather write that code, or I would pick AVL because that code's easier to write, that's too subjective. There are sort of objectively right and wrong answers when we're talking about optimality as far as runtime or memory usage, if that kind of helps. Great. Okay. Well, go away. Will the exam follow the same format as the practice exam? Okay. Yes? Yeah, I think we'll just say yes to that. Yes. The practice exam was made by the same group of wonderful TAs that helped write the exam with the intent of giving you an example of the format. Okay. There are 2 questions on the exam. I will tell you that. They have a lot of subparts, but there's technically 2. Okay, great. Okay. Oh, this is interesting. If you're having any weird grade scope issues, I will say too, please post to Ed. We have more TAs that are available to answer your questions on Ed. And if you aren't sure, you can always make a private post and show us what you're seeing. Okay, great. I feel... if you have DRS stuff, the DRS department handles all of that. I send them the exam. They will take care of it. They are superstars. I honestly have nothing to do with DRS because they are such superstars, so we trust them. Great. Okay. Okay, sweet. Good questions. Please feel free to ask more questions. The TAs are here to answer your questions on Slido in the background. If you have any other questions, please feel free to post on Ed. We'll be trying to keep a close eye on it between now and the midterm. Please feel free to ask clarifying questions about any of the conceptual stuff in lecture, et cetera, to start. Cool. Okay. Great. This is just a review slide, whatever. We're talking about heaps. Okay. So at the very end of lecture on Monday, today's Wednesday, we were starting to talk about, now that we kind of understand the rules of a heap, how do we perform what we need to do in order to implement the priority queue ADT? So remember, for a heap, we're specifically trying to implement the priority queue ADT. The priority queue ADT allows you to add items into it and remove the singular smallest value, remove min. Those are the 2 big pieces of functionality. At the end of lecture on Monday, we talked a lot about how to do remove min. If you remember, it was like, take the overall root, remove it, replace it with the bottom leftmost node, and then percolate down until the heap invariant is restored. But we didn't get a chance to talk about how to implement add. So add follows similar logic to remove min, where we are going to maintain the heap structure invariant and percolate in order to fix the heap ordering structure. So again, the opposite of the self-balancing trees, we maintain the structure property first, and then we fix the ordering after. So the way that we would implement add then, we are going to add a node to maintain the completeness invariant. So remember, there is always like one specific place where we add any new node to the tree. It is on the lowest level, as far to the left as possible, so we don't add any gaps. So in this case, that would be right here. We are going to add the node, and then we are going to do a set of percolations from the path from that node all the way possibly up to the overall root until we finally satisfy that requirement that any node is smaller than its children. So 3, we compare it to 8. 3 is smaller than 8, so we swap them. We percolate it up. Then we look at 3 and 4. We say 3 is smaller than 4, so we percolate it up. Then we look at 2, and we say, oh no, 2 is smaller than 3. I found where I belong. I sort of stop percolating. Any questions on that? Yes? What a good question. How do you find where the next where the next thing's supposed to exist? Here's what I'll ask you. So far, I have only shown you heaps looking like a binary tree. The way that I would find it if it was a binary tree is I would have to binary linearly search through and find where this gap is. It ends up being an end runtime, but in a few slides, foreshadowing, I'm going to show you how we implement this where we can always know where the next open spot is in a very convenient way. So I promise you, it's coming. Great. So the worst case runtime is similar to remove min. We might have to do at most log n swaps because log n is the height of the tree. So if it goes for all the way from the bottom level all the way up to the overall root, that would be log n swaps. So our worst case runtime is that we insert the new smallest value, and then we have to swap all the way up. Okay, so why don't y'all do some practice? Go ahead and draw a heap where you would add these values in order to the heap. We've got time. Go ahead and take 4 minutes and do this and draw it out together. All right, take about 60 more seconds, and then we'll check in, and I want to know the final state of the heap after you do all of these insertions in order. All right, let's talk about it. So, hang on, let's see. So, we start and we put the 5 in. 5 starts, that is just a valid heap all by itself. Now we are ready to put the 10 in. Where does the 10 go? Anyone? Left, to the left of 5. That's just where it's supposed to go. Do we need to do any percolations? No, I agree. Great. Now, where do we put the 15? To the right. I agree. Do we need to do any percolations? No, I agree. Okay, now we put in the 20. Where does the 20 go? Why, projector? To the left. Yeah, to the left of which node? 10, because we've completed that second row. Now we can start to fill up that third row. Now we need to put the 7. Who is going to become the parent of 7? Why? 10. What? Mysterious. Okay, do I need to do any percolations? Yes. Whoa, thanks. There we go. We percolate up. Do I need to do another percolation? No. Sounds good. Okay, now, where does the 2 go? I heard 15. Yeah, left of 15. That's where it goes. Do I need to do a percolation? Yes. Great. We percolate up. Cool. Do I need to do a percolation? Yes. Great. Ha-ha. There we go. There's our final results. Does anyone have any questions? Okay. All right. So hopefully we feel, oh, yes, please. Correct. It does not matter the order of the left or right children. The one time it does matter is that when you are not percolating up, there's only one option, right? But when you're percolating down, you always swap with the smaller of the 2 nodes. That's the one time between left and right matters. It doesn't matter if it's on the left or the right, but when you percolate down, make sure that you always swap with the smaller of your 2 children. Otherwise, you can get some weirdness. Yes? With the, sorry? With the other 12? Child. Oh, no. I mean, you're just comparing yourself with your one parent during percolation ups. Percolations down, you're comparing yourself with possibly your 2 children, so that's why you would pick the smaller of the 2 children. But when you're going up, you only have one parent in this sad half-orphan family tree situation. Yeah, cool. Okay, so how does this mean as far as run times? So for remove min, remember we remove the overall root, then we find the last node in the tree and swap it, and then we do some percolations. For add, we insert the new node into the available spot, and then we percolate to fix it. So the percolations at most travel the height of the tree. So all of the percolations at worst are a log n runtime. But in both of these, we have this find last node in tree or find next available spot. And it might not be obvious, or to our friend's previous question, like, how do we do that? I will tell you with the tree situation, what we would have to do is we would have to do a tree linear traversal where we just like recurse over everything looking to find that magical spot. And so that could end up with a linear runtime unless you do something very clever. So keep the structure of a heap as a tree in your mind, but no one actually implements trees with heaps with trees. No one makes nodes and like does the references. Instead, what we do is we store the values in an array and we use a set of equations to tell us how to get from any given index to either its parent or its left child or its right child. The way that this will work in order to make our math nice and clean is that we fill up our array starting with the overall root. So the overall root or the minimum value will always be at index 0 in this context. Then we fill up the array going from top down, left to right. So you can see I sort of designed this tree to make this array look really nice. So it would go A, B, C, D, E, F, G, so on and so forth. This is why, I remember on Monday I was like, don't worry about morphing the nodes. The nodes are just in your mind, as it turns out. The array is still representing this, but we are really only storing the values in an array. And when we're doing the percolations, that means we're just actually swapping entries in an array, which is much more efficient than swapping data fields within a node. Here are those magical equations. That's the word I'm looking for. So peak min, what's an array at index 0? Great. Constant time lookup. But it was already constant time with the tree, right? We were just looking at over root. Now we look at index 0. So how do we find the last node? Well, now, in this case, if we're always filling from left to right, we know that the last valid node will always be stored at size minus 1. So this is, again, a situation where we have an underlying array as the structure, which has its own internal capacity, and then we must have a separate size field that tells us how many things we've actually put into the array. That means that if we fill from 0 forward, that the last possible thing, the L in our case, is at size minus 1. That means there's 12 items in here because we use 0-based indexing. We can find the last element at index 11, 12 minus 1. Which means what was previously a linear runtime to like move through the tree and find stuff is now a constant time lookup. Oh, amazing. We're so impressed. We love heaps already. Okay. This also means that in order to find the next place to put our node in the add context, it's at size. So again, we don't have to loop through and find the gap. We literally just ask ourselves, what's the next available spot in the array, which is at size, because we're using 0-based indexing. Does anyone have any questions about those pieces before I get into the children and parent equations? Cool. So then, to do some handy-dandy math, for any given child, to find its left child, so let's say we're trying to find A's left child, we put in 2 times the index I'm at plus 1. So A is at index 0, 2 times 0 is 0, plus 1, index 1, there's the B. Great. Same thing for the right child except plus 2. So 2 times 0 is 0, plus 2 at index C, or index 2 is C. Great. Let's pick a different one. Let's go to E. E is at index 4. 2 times 4 is 8, plus 1, there's the J, right there, it's left child. Plus 2, there's the K, it's right child. Yes? Yes. This array will never have gaps. Yes. Because we do not allow gaps in the tree, that is how we will not have any gaps in our array. So you must always have all indices of the array full from index 0 to size minus 1. That's the same sort of way of representing no gaps. So if you do some algebra to just reverse those equations, to go from child to parent, say when you are percolating up, then if I just want to find, like let's say I want to find I's parent, I is at index 8. We do 8 minus 1, that's 7. 7 divided by 2 is 3, because we do integer division. And that's how we find the D. Any questions? This is how you will be implementing your heaps for project 3. You will not be making nodes and references. You will be making an array. You will be using these equations. I used to have another slide in here because somebody always asks, well, I've seen heaps implemented where they, instead of filling up from 0 onwards, just sort of ignore 0 and fill up from 1 onwards because they think that makes the algebra look better. You might find that on the internet, ChatGPT. That is not how we are implementing our heaps in this case. But it is merely just a different way of doing the math. It is the exact same concepts. Great. Let's talk about runtimes then. So the array-based heap, the add then, because we've eliminated that linear runtime to find where we would place the new node, that got transformed to constant. So now its worst case runtime is truly just the log n, which is great. We're back at that sort of logarithmic runtime because it is still a tree-based structure. Remove min, same thing. We eliminated the linear runtime, so now its worst case is log n. Now you can see here, we also have this sort of worst versus in practice. This is about the likelihood of how far something's going to have to percolate. If you add in a new minimum value, it will start at the very bottom row and have to percolate all the way up to the very top. That's a logarithmic runtime. But it's actually pretty rare that you've added in a new minimum value unless you are particularly inserting in, say, like decreasing order. Well, then you're always adding the minimum and you're always going to hit the worst case runtime. So, you know, the order in which you add things does matter. But if you have like a perfectly randomized, you know, order in which you add things into the heap, it's not very likely that the node will always be the minimum value and thus have to percolate up. And because of the way that trees are structured, right, half of the nodes of any given tree are always in the bottom level. So that means that it is not likely that the nodes have to travel too far up the tree. And so you end up with an in-practice add of what we would consider to be constant. Because usually it only has to percolate up like 1 or 2 levels kind of thing. But worst case runtime is log n. So if somebody asks you, you would say it's a logarithmic runtime to add, but we usually get better performance than that. So we have now matched the asymptotic worst case of the AVL tree. Great. AVL does have different functionalities. We usually use AVLs for dictionaries. We usually use heaps for priority queues, but the runtime of getting things in and out is similar. But that is from big O analysis. And if we remember way back from week 1, when we talked about that contiguous versus non-contiguous memory, since we are just navigating around within the indices of an array, the constant factors are way better. And so actually, we end up with a very performant structure because we are using the concepts of a tree, but stored within an array. So the in-practice case for add is really good for heaps, as it turns out. Yes? Oh, is there an AVL implementation of array? I do believe that you can go on the internet and find array implementations of AVLs, but because of all of the crazy rotations, it is even grosser code than the node-based one. Yeah, and it's mostly empty. It is not considered a good enough trade-off that the convention is that we don't bother with the array implementation. But because we have these sort of like gentler requirements of the heap, then the array is a really good fit. Oh, really? Love that. Okay. And a heap is much simpler to implement. See, if you take CSE 332, they make you implement an AVL. But Casey makes you implement a heap. You're welcome. You're welcome. Okay, great. Okay, just so you know, these next few slides, I don't actually mean to like present them to you. These are literally just notes for you for the project. That's why they're like these massive blocks of text. So you can read these as you go along with your project. So there's lots of tips, all of that sort of good stuff. I'll let you read it as you get into the project. This is me just saying, hey, look at these helpful things. You should look at this when you're implementing your P3. Great. Okay. Great. Okay. To wrap up Heaps, we're going to talk about one more piece of this. We are actually going to end up using priority queues a lot, as it turns out. Priority queues are really useful ADT because it lets you sort of order things according to how the compare to would distribute them. So it's really nice to have this sort of queue where it, like you put things in and then it spits out either the smallest or greatest number. It actually ends up being one of my favorite sorting algorithms because it's in place and really efficient. So we are going to talk about one more aspect of Heaps that make them even more performant. So in the previous example, I gave you a sequence of numbers, and you added them one by one into the heap. It was good. Practice your percolations, do all that stuff. But let's talk a little bit more about some really fun math that I hope will prove to you that actually even that sort of build heap situation that you do, we can actually end up with an even better runtime. So if I asked you to build heap like I did before, where I give you just a set of elements, given n elements, we could just call insert n times. And so the worst case runtime would be n log n, right? It's log n, worst case runtime for each add. We have n items, n log n. It's our worst case, which is not a bad runtime to fill up our heap. But that is based on the idea of the worst case add runtime. And remember, I just talked to you about how the in practice is actually a lot better than that. Because when you add everything into the heap, not everything is going to percolate all the way up. And if we kind of pay attention to this and do all of these adds all at once, instead of adding something, like let's say we were adding in descending order, so that every time we added something, it really was the minimum value, and we really have to do that logarithmic all the time up, that would be really inconvenient because we know then we're sort of doing a lot of extra percolations. What if, so there we go, that's what I just said. Great. This is also mostly just text for you to read that I just said it aloud. Can we do better? What if instead of treating each of those inserts as totally independent things, we dumped everything into the array all at once, and then we did a series of percolations that only force the things that really need to go up to the next level, up to the next level. This is predicated again on the idea that we're like, well, the majority of any tree lives in its leaves. That's just the exponential growth nature of the tree. So the majority of the leaves will probably stay on the bottom level. And instead of accidentally putting them in descending order and doing all these percolations, can we just dump everything in and only percolate up what needs to be percolated up in the final state of the tree? This is called Floyd's build heap algorithm. Yay, another man invented an algorithm and put his name on it. Invent algorithms. I want to say your name aloud in class, please. Okay, the way this works. Let's build a tree with the following values. We just started with a list of values. We knew all these values to start with. We fill up the array in whatever order they gave us for the values. Here is the mental model of what the tree might look like, but it's actually in the array. Now, hopefully we know we implement with an array, but we got to draw the tree to help ourselves. So that's the tree that gets formed. Now, this is weird, but what we are going to do is we are going to call percolate down on every single one of these things, starting from the back forward, which feels very silly in this first row. So in this first row, 6 can't percolate down, 7 can't percolate down, none of those things can percolate down. There's nowhere further to go, which actually is great. So essentially what we've got is just a bunch of constant runtime calls to percolate that are just don't move. So that's a bunch of constant calls. Now, we transition to the next row up, or level 3 from the top, if you will. And we look at 9, 9 doesn't percolate down. We look at 2, 2 doesn't percolate down. 10, aha, we finally have our first percolation. So we've managed so far to lock this number of items into their final resting place in the heap without doing any percolations, with doing one percolation if you want to count that 7 there. We get down to the 3, no percolation. Great. We have just locked in levels 4 and 3 without doing any percolations, and that's the majority of the values in the tree. So we do another one here. This one will trigger a percolation. We're going to leave it for right now. There we go. We percolate it all the way down. We're not going to percolate up. We're percolating down, right? So let me go back real quick. The 11 needs to percolate down. We now ask ourselves continually, is 11 still not in the right spot? It's still not in the right spot, so there's one more percolation. Now we've got 11 in its final resting place. Great. Now we come over here. We ask 5 to percolate down. It's got to do a percolation. It's got to do one more percolation. Great. Now 5 is in its final resting place. And then we come back around, and we finally do our level 1 percolation. Remember, we always swap with the smaller of my 2 children. And there you go. So as you can see, yeah, there were some percolations, especially as we got closer to the top of the tree. But we know there's just fewer nodes living at the top of the tree. So by dumping everything in and calling percolate down, starting from the back, moving towards the front, we end up with very few percolations to build up this tree. And if you are a math person, you can read through all of these slides that hopefully will do the algebra to prove to you that actually what we just did ran in linear time. So instead of inserting them one at a time, by dumping them all in and doing the percolate down from each level, we went from n log n down to linear, which makes this an exceptionally efficient structure. The basics behind this math is you do a bunch of sort of summation analysis of how far each individual node runs, and when you combine all the just possible levels it needs to travel, the algebra works out to give you linear runtime. That's the TLDR of it. Great. There are some operations I didn't talk about. They are part of your programming assignment. They're about if you once something's in the tree, need to go in and change its priority, but it follows the same concepts of percolate up and down. I've also written a bunch of sentences in here for when you're doing your assignments to help you out. But I'm going to end it there. Congratulations. You're now ready to do Project 3. Best of luck for P2. Please start preparing for the midterm. Go to section tomorrow. And I will see you and all of those mysterious creatures I only saw on the first day here on Friday. Thanks so much, everybody.